Today we will be talking about how Windows handles deadlocks. Deadlock prevention for Windows. Never wait on a kernel dispatcher object in any driver routine that can be called at IRQL equals dispatch underscore level. Routines that can be called at IRQL equals dispatch underscore level include IO completion routines and the IO dispatch routines of storage drivers and USB hub drivers. If in doubt, use the assert macro on a checked build to test for the IRQL at which the routine is called. Disable normal kernel mode APC delivery before calling any of the executive resource acquisition routines and before calling kwait XXX to wait on an event, semaphore, timer, thread, file object, or process. In a device driver, call k-enter critical region and k-leave critical region to disable and subsequently re-enable APC delivery. In a file system driver, call fsrtl enter file system and fsrtl leave file system. Use the driver verifier, verifier.exe, deadlock detection option to find potential deadlocks. This option is available on Windows XP and later releases of Windows. Always establish and follow a lock hierarchy in code that acquires more than one lock at any given time. Following attributes are for deadlock detection. Driver verifiers deadlock detection routines find lock hierarchy violations that are not necessarily simultaneous. Most of the time, these violations identify code paths that will deadlock when given the chance. To find potential deadlocks, driver verifier builds a graph of resource acquisition order and checks for loops. If you were to create a node for each resource, and draw an arrow anytime one lock is acquired before another, then path loops would represent lock hierarchy violations. Driver verifier will issue a bug check when one of these violations is discovered. This will happen before any actual deadlocks occur. Note, even if the conflicting code paths can never happen simultaneously, they should still be rewritten if they involve lock hierarchy violations. Such code is a deadlock waiting to happen that could cause real deadlocks if the code is rewritten slightly. When deadlock detection finds a violation, it will issue bug check 0xC4. The first parameter of this bug check will indicate the exact violation. Possible violations include 1. 2 or more threads involved in a lock hierarchy violation. 2. A resource that is released out of sequence. 3. A thread that tries to acquire the same resource twice, a self-deadlock. 4. A resource that is released without having been acquired first. 5. A resource that is released by a different thread than the one that acquired it. 6. A resource that is initialized more than once, or not initialized at all. 7. A thread that is deleted while still owning resources. 8. Starting in Windows 7, driver verifier can predict possible deadlocks. For example, trying to use the same kspin_lock data structure both as a regular spin lock and as a stack queued spin lock. Deadlocks on different levels occur when resources are exclusive. When debugging a deadlock, it is important to note whether or not the deadlock is on a kernel level or a user level. Steps to follow when a deadlock occurs in user mode. Issue the nstexts.locks extension. In user mode, you can just type locks at the debugger prompt. The nstexts prefix is assumed. This extension displays all the critical sections associated with the current process, along with the ID for the owning thread and the lock count for each critical section. If a critical section has a lock count of 0, it is not locked. Use the thread status command to see information about the threads that own the other critical sections. Use the kb display stack backtrace command for each of these threads to determine whether they are waiting on other critical sections. Using the output of these kb commands, you can find the deadlock, 2 threads that are each waiting on a lock held by the other thread. In rare cases, a deadlock could be caused by more than 2 threads holding locks in a circular pattern, but most deadlocks involve only 2 threads. There are several debugger extensions that are useful for debugging deadlocks in kernel mode. The kdex.locks extension displays information about all locks held on kernel resources and the threads holding these locks. In kernel mode, you can just type locks at the debugger prompt, the kdex prefix is assumed. The clocks extension displays the state of all queued spin locks. The wdfkd.udf spinlock extension displays information about a kernel mode driver framework, KMDF, spinlock object. The deadlock extension is used in conjunction with driver verifier to detect inconsistent use of locks in your code that have the potential to cause deadlocks.